Welcome once again to the REMA webinar presented by Thermo Fisher Scientific, Unlocking Efficiency, Mastering Handheld XRF for Smarter Scrap Metal Sorting. Just a few housekeeping things before we move into Dr. Matthew Bauer's presentation. We also have a code of conduct which will be put in the chat by my trusty colleague Annette. Feel free to download or read at your leisure. All views expressed during the webinar are that of Thermo Fisher Scientific as well as its speakers, not of REMA. And also we have with us today Dr. Matthew Bauer, who is an experienced expert in analytical chemistry with nearly 25 years across a broad spectrum of technologies, including NIR, FTIR, ICP-OES, MS, XRF, which we're here for today, and NLibs. He holds both an engineering and a master's degree in chemistry from the University of Strasbourg, as well as a PhD in analytical chemistry from the University of Hamburg. As the senior application scientist for Thermo Scientific's Niton Analyzers product line, Matthew plays a pivotal role in supporting handheld XRF and LIBS technology. He collaborates closely with commercial teams and end users, helping to expand applications and develop new markets for these portable solutions. His deep technical knowledge and practical insights make him a valuable contributor to advancing innovation in elemental and materials analysis. And with that, I would like to turn it over to Dr. Matthew Bauer.
Thank you very much, Matt, for your kind introduction. Good morning, good afternoon, ladies and gentlemen. Welcome to this webinar about a technology that is very commonly used in metal recycling. It's handheld X-ray fluorescence spectrometry, or XRF. In fact, our team introduced the first handheld XRF analyzer about 31 years ago under the name Niton XL, making it possible for our customer to get lab quality results where they need it. So let's get more about what you can do using this technology and how to improve efficiency by mastering handheld XRF for smarter scrap metal recycling. So we'll cover the following topic today, and we'll start with some of the key success factors in scrap metal recycling. Then we will have a review of available technologies for metal and alloy testing. After that, we will cover more in depth the technology itself, handheld X-ray fluorescence spectrometry. We will then have some real-life examples for alloy grade ID for scrap sorting. And then we will present some new features for enhanced lightweight metal sorting. After that, we will share some good practices and wrap up the webinar presenting our solutions. So what are some of the key success factors in scrap recycling operation? The first and probably most important key success factor in metal recycling is to increase the value of scrap by accurate sorting the different grades and also trading scrap at the best price. A second key success factor is to increase the speed and the efficiency of scrap sorting using, for example, modern equipment and technologies. Another key success factor, especially for foundries, is to improve quality by, for example, detecting tramp elements as well as removing impurities as well as complying with stringent regulation. All this actually emphasizes the importance for recycling industry to deploy some analytical testing method for fast and accurate scrap sorting. So there are multiple possibilities for testing metals and to identify the alloy grades. So one first family of methods are actually purely qualitative, and they include visual inspection as well as magnet testing. Other possibility is spark testing using an angle grinder or chemical tests using acids or other chemical. Unfortunately, none of these techniques can be used for all type of metals, and those are often relatively inaccurate. Therefore, those methods are mostly obsolete, and spectroscopic methods are preferred. Among the spectroscopic method, we have mobile optical emission spectrometry that can be brought to a scrapyard, but the technology itself is made generally of two modules, which make it relatively difficult to maneuver. So the probe itself is relatively small, but the other module has to be carried with a backpack or with a trolley, making it relatively difficult then to achieve high sample throughput because of the poor maneuverability. Then we have the last family of technologies, which are handheld technology. We have the handheld X-ray fluorescence spectrometry, XRF, as well as the handheld LIBS, laser-induced breakdown spectroscopy. Both technology are very compact, like gun-shaped instruments, which are very easy to maneuver. Both come pre-calibrated and work in a point-and-shoot way. The XRF is generally slightly more accurate in general and is also more tolerant to the state of the surface, both in terms of cleanliness as well as irregular shape, while the handheld LIBS is more sensitive to the state of the surface, but can deliver the results for magnesium in aluminum, for example, in shorter measurement time. So what is handheld XRF and how does it work? XRF is an acronym standing for X-ray fluorescence spectrometry. And what is the principle of the technology is that we have a miniaturized tube that irradiates some atoms at the surface of the sample. Those atoms will absorb the radiation from the X-ray, which will cause actually an electron close to the nucleus to be ejected, and the resulting vacancy will be actually filled by an electron from an outer shell. And during this process, there is a secondary X-ray that is emitted, which is called X-ray fluorescence, which is then also specific for every element. And this secondary X-ray will create some electric pulse in a semiconductor detector, and the digital signal processing chain will then count the frequency of those pulse, of those events, which yields actually to a spectrum. The spectrum is then processed by algorithms, which then calculate the chemical composition of the material and display it in real time on the screen of the analyzer. So modern handheld XRF analyzer can detect either elements from chlorine to uranium when they use a so-called silicon pin diode detectors, or from magnesium to uranium when they use some so-called silicon drift detector. Handheld XRF is a method of elemental analysis that will provide information about the presence and also the total concentration of all these elements, regardless of their oxidation state, or regardless if they are bound in some molecules. So the analytical data are generally generated in form of spectra, and there are typically 1 to 4 X-ray lines per element that are detectable, and those are actually tabulated here in small character in this periodic table. So on the figure on the left-hand side, we display here spectrum of a stainless steel 316 grade. The spectrum is a bit like the fingerprint of the material. So the energy of the photons are plotted on the x-axis, and since the energy is element-specific, that provides us an information about which elements are present in the sample. On the y-axis, we have the count rate, and the count rate provides us an information about how much of each of the elements is present in the sample. And as you can see on the spectrum here, we have peaks for chromium, iron, nickel, and molybdenum, which are actually the main component in the stainless steel 316 grades. So when processing the spectrum with algorithm, we can calculate the chemical composition, And when comparing the chemical composition with tabulated value, we can also identify the grade of alloy, here stainless steel 360. So the Handheld XRF use libraries of tabulated value for the common industrial alloy grades. And so those tables include interval of composition for the alloy grades. The standard library includes more than 500 grades according to different standards such as ASTM, AISI, Aluminum Association, or Copper Development Association. The library can be augmented by the user and contains already really many different family of alloys that are listed here at the bottom of the slide. So pure elements, low alloy steel, stainless steel, tool steel, and many alloys of base metals, as well as solder or exotic alloys. So the library can be customized by the user, and it has also been translated into different standards, such as the European German DIN standards or the Chinese GB standards. So it's also important to correctly interpret the result in terms both of alloy grade ID and chemistry. First of all, when we look at the chemistry, the elements are displayed in different colors, and there can be some labels. For example, a red label will indicate that an element is outside the interval of specification of the identified grade, as well as another label, the blue label, which indicates actually that the element hasn't been specified for the identified grade, and that could be an indication that it's a tramp element. Very important is also the match number. When it's lower than 1, it's considered to be an excellent match. So it means that all the elements are within the range of the specification that is given in the library. When there are some elements that are a bit borderline, it becomes a good match. When one element is a bit slightly off, it becomes a possible match. And when the difference is too high between the measured composition and the alloys in the library, the statement no match is displayed. So a frequent question is what type of accuracy can be achieved using Handheld XRF technology. And this slide actually illustrates the results obtained out of the box for sets of certified stainless steel sample, as well as a set of super alloys, which are alloys made of cobalt and nickel as element base. And for all 4 cases, as you can see, there is actually an excellent correlation between the certified values and the measured values, which is given by the R-square correlation coefficient, as well as a slope that is close to 1, which indicates actually that there is a very low systematic error or bias. Finally, we have also calculated the standard error of estimate, which is pretty low both in relative terms as well as in absolute terms. So from these results, overall, one can state that Handheld XRF really delivers lab quality results. So let's now have a closer look at some real-life cases of alloy grade ID commonly found in scrap sorting. So we have listed here some features of Handheld XRF for alloy analysis. So the instrument come pre-calibrated with so-called modes. So for example, the general metal mode is dedicated for the analysis of industrial alloys. It covers an element range from magnesium to bismuth. The standard spot size is 8 mm, and on some instrument, you can also have a deployable collimator of 3 mm to make more focused measurements. The measurements are typically done in 1 or 2 sequences, also called filters or beams. And so during the first sequence, we measure a first range of elements from titanium to bismuth. Those are the main range elements or the heavy elements. In the second sequence, we measure the light elements from magnesium to sulfur. As we've seen in the previous slide, the results are near laboratory grade. The technology itself is non-destructive. There is generally no to little sample preparation that is required. The technology is also very tolerant to irregular shape, thanks to normalization to 100% of the detected concentration. And it's also a method that is very easy to operate and to maintain. There are a few drawbacks. For example, Handheld XRF may be slower than LIBS for the detection of magnesium in aluminum, and also it's unable to detect carbon and elements with atomic number lower than magnesium in any type of material. So in scrap sorting, measuring elements from titanium to bismuth is generally sufficient to identify many metals and alloys. Those are listed here on the left-hand side. The typical measurement time for a simple grade identification is 1 to 3 seconds based on these heavy elements, while for more accurate measurements or to detect trace and minor trace elements at trace or minor level, it can be necessary to extend the measurement time beyond 3 to 30 seconds. So here are some examples of the main strengths of Handheld XRF with the ability of measuring very quickly all the elements from titanium to bismuth and identify really various alloy grades within a couple of seconds. That's, for example, the first two cases, which are grades of stainless steel, 304 and 316, which are different in their nickel and molybdenum content that can be very quickly measured using the technology. Also, brass or nickel alloy can be very quickly identified, and even some aluminum alloys can be identified within a couple of seconds based on heavy elements like, for example, copper and zinc for the 7075 grade. So overall, yes, the grade ID based on heavy metals can be completed within 1 to 2 seconds. So then we have seen that the previous slide, that's almost 90% of the alloy grade present in the library can be identified upon the heavier elements, but in some cases it's also necessary to measure light elements. That's, for example, the case for magnesium alloys, which should systematically be identified upon light elements. It's also the case for some aluminum alloys. That's, for example, grades that differentiate only upon their magnesium content, such as 5052 and 5086 grade, or to differentiate numerous cast aluminum grades, such as, for example, A319 from some wrought aluminum grades based on the difference in silicon and magnesium content. There are also a few stainless steel grades that need the measurement of light elements, such as, for example, the 177 precipitation hardening grade that contains about 1% of aluminum that may mix up with 301 grade if light elements are not measured. That's also the case for stainless steel 303 that contains 0.3% sulfur versus 304 that doesn't contain sulfur but has the exact same composition for the other alloying elements. Also, most copper alloys can be identified without light element. Few exceptions are, for example, pure copper that differs from the aluminum bronze C642 only upon the aluminum and silicon content. Therefore, actually, we don't need really to measure the difference because pure copper is red while the aluminum bronze is yellowish, so that they can also be differentiated not only via the chemistry but also via their aspects. Then for super alloy and titanium alloy, although those alloy bases often contain light elements. The measurement of light elements is generally not a must to identify the different grades. When light elements are required, it generally takes a longer time. So instead of between 1 and 3 seconds, it takes, generally within 6 seconds, sometimes slightly longer. Also here, for higher accuracy measurements on minor and trace elements, one has to extend the measurement time. Here are some examples of grade IDs involving light elements, and the question is, do I really need the light element capabilities to identify those grades? So a first example is a titanium 6-4 grades, which could be identified within 2 seconds without measuring the concentration of aluminum. There on the screen, the right grade alloy is identified within 1.8 seconds, and the nominal concentration of aluminum is also displayed as LEC, which stands for light element content. So we need then a bit longer time, about 6 seconds, to detect aluminum, also with a pretty high precision. So in this case, it's not a must to detect the light elements. That's also the case for some grades that contain elements that XRF can't detect at all. For example, we have here a beryllium copper grade C172 that can be identified upon the cobalt and copper concentration, and also display here the nominal amount of beryllium at 1.9%. One case for which measuring light element is a must is the cast aluminum A319 grade, because when measuring only a main element range, so the heavy elements, there is a risk of mix it up with the 2014-2017 grade, and therefore it's a must to measure the light elements, silicon, to identify properly this alloy and also improve the accuracy. So here we have seen that light element is sometimes a must, but for most cases, actually, it's not needed. When we talk about light elements, we've seen in the previous slide that it can be pretty significantly longer to identify grade based on light element, and therefore we have released some enhanced feature to identify the grades of lightweight metals. This is in a form of a new mode, which is called light metal quicksort mode. So it's a mode that emphasizes on the analysis of lightweight metal, and it uses a reverse logic versus a general metal mode. So instead of first measuring the heavy elements from titanium to bismuth, we first measure the light elements as well as the first transition elements from titanium to zinc. And in the second phase, if needed, we can measure the heavier element. In this way, most aluminum and magnesium alloy can be actually identified using the first sequence or first filter. So we have a specific alloy library that is focused on the lightweight metal. It includes 61 alloy grades and families of alloys. So we have 8 families of alloys for base metals. We have 8 common grade of magnesium alloys and 45 common grades of aluminum alloys in this library. Magnesium, which was long time the most challenging element in Handheld XRF. Historically, like 10 years ago, it took about 10 to 20 seconds to detect magnesium at a level of 0.5%. Now, with using this mode, it's possible to measure magnesium pretty accurately within 3 seconds of measurement time. And in this way, as you can see on the right-hand side, we can differentiate also some grades that mostly differentiate based on the light elements, such as, for example, the grade 1100 from the grade cast aluminum 356 from 6061 and 6063 that differentiate mostly upon their concentration of magnesium and silicon. So in this way, we can identify actually most aluminum and magnesium alloys within the first 2 to 3 seconds, and their weights also equal or even exceed the capability of LIBS, given additionally that LIBS often needs several measurements to be done to compensate for heterogeneities. So here is a short video to demonstrate how fast the identification of aluminum alloy can be done. And as you can see here, we identify within less than 2 seconds a grade of 6063 containing only 0.5% magnesium and about 0.5% silicon. Then we have another example here of a cast aluminum alloy that also can be very quickly identified within 1 second and detect actually the concentration of magnesium within about 3 seconds. So that's just to demonstrate how fast and revolutionary this mode is to sort the aluminum and magnesium alloys in the scrapyard. Excuse me. I will share now some best practices when analyzing metals and alloys using Handheld XRF. So here, the first case is the analysis of turnings. The Handheld XRF can be aimed directly to the turnings, even if those do not fully cover the instrument aperture. And as there is a normalization to 100% of the detected concentration, the results actually will be accurate. More important when analyzing turning is to have what is called detector protection, also called ProGuard on thermal Fisher products, so that it prevents the puncture of the detector window. So the light elements, which are also more sensitive to the shape, actually should not be measured, because measuring the light element can actually negatively impact the accuracy. So this is one of the few cases where the analysis of light elements is detrimental to the accuracy of the measurements. Then a second important point one must keep in mind is that XRF is a method for measuring the composition at the surface of a sample. It means that all contamination at the surface will have a higher weight in the final result. So for example, a thin layer of dust will have almost no impact for the heavier element from titanium to bismuth, while it will absorb some of the lighter elements. Also, the presence of lubricant, which may contain some of additive elements listed here. Among those, it could be, for example, molybdenum, which then would be detected as a false positive and cause mismatch in alloy grade identification. And so for these cases of sample having either dust or presence of lubricant, it's advisable to clean those using a solvent that evaporates fast, like, for example, isopropyl alcohol. Also, severe rust can affect the accuracy of all the elements, as well as paints and all type of metal coating. So those coatings can cause false positives and then also misidentification of the material, and therefore it's necessary to remove the layer of coating or rust using, for example, a grinder. And therefore we recommend to use grinding paper made of zirconia and alumina, which is good probably for in 99% of the cases for all type of metals. There might be one exception, is for some aluminum alloys, especially those containing low zirconium, where pure alumina grinding paper can be preferred to avoid false positives of zirconium and misidentification, for example, of 7050 grade, which contains low level of zirconium. Then a further interesting case is actually the analysis of cast aluminum with silicon content being higher than 12%, that are so-called hyper eutectic alloys. And so during the solidification of the melt, there is a volume shrinkage that pulls the remaining liquid. In this case, it's aluminum from the center of the material toward the surface. And this causes actually a depletion of silicon at the surface, which itself causes reading being 1 to 2% lower for silicon. So that means about relatively 10 to 20% underestimation of the silicon content. Unfortunately, in this case, grinding the sample actually doesn't help because the depletion of silicon is actually pretty thick, and the only way to get an accurate result is actually to cut the sample and measure the sample in its core. So precision is also an important parameter. It's generally expressed as a multiple of the standard deviation, and the standard deviation of a measurement follows what is called a counting statistic. So it means more counts measured, better will be the precision. And so this figure of precision will depend on the tube power and its voltage, as well as on the detector technology surface, so basically on the hardware of the instrument, as well as on the measurement time. And so when one wants to double the precision, in other words, cut the standard deviation by half, one has to quadruple the measurement time, since the standard deviation is proportional to the inverse square root of the measurement time. So now in the following, I will present the solution offered by Thermo Fisher Scientific for the scrap metal recycling market. And we have a full range of analyzer that will meet very different user needs. And the three most popular models for metal recycling are the Niton XL2 100G, the Niton XL2 Plus analyzer, and the Niton XL5 Plus analyzer. And this table summarizes the specification of our most popular analyzer. So the XL2 100G uses a 2-watt tube with a silicon pin diode detector, so it can only detect the elements from titanium to bismuth, while the XL2 Plus has slightly better tube, covering a higher range of voltage and current, and also it has a silicon drift detector, enabling the detection of light elements additionally, so the elements from magnesium to bismuth overall. Then we have also our premium offering, the Niton XL5 Plus, which is the smallest, lightest, and most powerful Handheld XRF analyzer available on the market, with a 5-watt tube and with 500 microamp maximum current, with a large area silicon drift detector. And this instrument specifically also comes with the mode for sorting aluminum and lightweight metals and alloys. So then when we want to have a look at which analyzer is suitable for which application, so the Niton XL2 100G is our value model, which stands for simplicity and ruggedness. It's also the most affordable Niton analyzer, which delivers actually great results in terms of accuracy for alloy identification based on the main elements. For the alloy that requires light element detection, then the instrument of choice is the XL2 Plus analyzer, which also, so this is, for example, the case to differentiate 303 from 304 grade, or to identify grades of cast aluminum. And so this instrument comes also with the ProGuard detector protection, so that's also more suitable for the analysis of turnings, while the XL5 Plus is the top-of-line instrument that is well suitable for rapid measurements of tramp elements and traces, as well as for the fast identification of lightweight metal using the light metal quicksort mode. So to conclude, Handheld XRF has numerous benefits for the metal recycling industry. It helps businesses to increase the value of scrap and optimize the trading value by sorting accurately all type of metal grades. Also, with fast measurement, it allows to improve the productivity of scrap metal processing operation, especially also for lightweight metal with a light metal quicksort mode. For foundries, it also provide a good way to remove impurities and to control the amount of tramp elements. So overall, Handheld XRF is a technology that is also very easy to use and to deploy. And it is also a very versatile method that can analyze many different materials beyond industrial alloys, such as, for example, precious metals, automotive catalyst for platinum group elements, as well as for the trading of black mass used in coming from the recycling of lithium-ion batteries. So overall, we can say it's an excellent tool actually for making faster decisions in the field with a high level of confidence. So for more information, if you wish to contact us, so please visit our website at thermofisher.com/Niton. And we are, of course, also looking forward to meeting you in person at the next RIMA next year in Las Vegas, and also in some regional events where you can connect with our experts that will be present at the booth and will be able to demonstrate our full range of products. Thank you very much for your attention, and I'm looking forward to answering your questions.
Thank you, Matthew. Yes, and with that, feel free to use the chat function for any questions that you have. We have a few to begin with. First one is from an anonymous user. Matthew, how often do I need to recalibrate my XRF instrument?
So the calibration itself is in the factory, and actually it's stable over years, and it doesn't need to be recalibrated in a regular interval, but therefore we have a function called a system check that will readjust the calibration. It should be performed almost daily, and that will also provide information if an instrument needs recalibration.
Thank you. Next up, we have, can XRF identify stainless steel 316L?
So the Handheld XRF, as we've seen during this presentation, it can identify 316 grade, but it cannot identify and make the difference between 316L and 316H, because that would need the detection of carbon. For the detection of carbon, LIBS is another technology we have also in our portfolio, is the technology of choice and can be used for this purpose.
Next, we have from Tori Salvato. How long to hold the trigger to catch a good reading?
So for generally, we have a built-in beep function. So when the analyzer identifies a grade, it will make a beep, and that will be sufficient to only identify the grade. And for having more stable results, it's of course advisable to extend sometimes the measurement time. So generally, depending on the hardware of the alloy, yes, 3 to 10 seconds is definitely sufficient to have a very accurate result in most of the cases.
Next, from Stephen Sheck, can the Niton XL2 100G accurately grade general aluminum alloys, or would you need the Niton XL2 Plus?
So the Niton XL2 100G can grade probably 75% of all aluminum grades. If those can be identified only upon their heavy elements from titanium to bismuth. So, but in case the grade can be only identified based on the light element, then it's better to use the Niton XL2 Plus.
Next up from Bobby, is LIBS becoming more popular, and is the only benefit the shorter analysis time for magnesium and aluminum? I would imagine this means more popular than XRF.
So LIBS became actually very popular for the aluminum sorting in the recent years. And now with the light metal quick sort, we actually can match the speed. LIBS is also generally, as I mentioned at the beginning of the presentation, more sensitive to the cleanliness of the surface and to irregular shape. So that overall, I believe, at least for samples that are not ideal, like in a scrapyard, XRF is more tolerant to this state of the surface, and therefore I believe it's the better technology for scrap recycling. Yeah.
Thank you. And this flowed into the chat, but just for everyone's benefit, this entire recording will be available by Monday afternoon at the latest. Maybe even a touch earlier. It will be emailed into your inboxes. Next up, we have from Batuhan Ozkan. Sorry if I got your name wrong, but in the Connect Date program, only 999 readings can be downloaded at once. This limit can sometimes be insufficient. Is it possible to increase it?
So that's for the if the pictures are also stored. So this feature can actually, if there is no picture stored, actually this can be extended as well.
Okay. And then last but not least, and this one, Matthew, you probably want to go back to slide 14 just for everyone's benefit. How can the analyzer show aluminum in AA7075 without measuring it?
Yeah, so that's actually, we are using the scatter produced by the spectrum. So a sample producing high scatter is a lightweight metal, and therefore we can make the assumption that it's aluminum without actually measuring the elements. And in this way, we can accurately identify many lightweight metal grades within the aluminum family, about, yes, 3 out of 4, without measuring aluminum itself.
Thank you. All right, calling last call for questions. Going once, going twice. Wait a little bit to see if any more flow into the chat. While we're waiting, I would once again like to thank Dr. Matthew. Oh, here we go. If calibration isn't required for many years, how can the same sample be measured differently by two different XL5 analyzers?
So you mean give different results between two different XL5 analyzer?
Be my interpretation as well. The way
Yeah,
you
so,
just, yeah.
Yeah, so that's actually should not be the case. And all I can recommend is to contact our service team. It's also advisable to measure in regular interval the check sample that we provide to also ensure that the calibration is still valid, beside then doing the system check and the system health check from time to time.
Okay. I don't want to be premature again. We'll just wait to see if anyone else's questions flow in. All right. Well, thank you, Dr. Bauer. What an informative and wonderful discussion. And with that, I want to thank all of our guests for their time as well. It was a great way to pass the last 45 minutes. And I hope everyone has a wonderful rest of fall and great holiday season. Thank you for joining, everyone. Have a great day.
Thank you. Have a good day.